All right. Okay, so we have the honor and the pleasure to have Paola Caselli with us, although virtually, but hopefully, as we said, someday also in person. Paola is the director of the Max Planck Extraterrestrial in Garching, specifically of Center of Astrochemical Studies, also honorary professor of University of Munich. She has a long history, so I won't be going through all the places and things she's done, just mention just few. In 2018, she's been Jubilee Professor of Chalmers University in Gothenburg in Sweden, which is a very nice place. I visited recently. I advise everyone. Since 2018, she's a guest professor at Onsala Space Observatory in Sweden also. And in 2020, she was the Balau Professor of University of Groningen. She spent quite some time at the CFA as a pre-doc and postdoc also, as some of you have seen. She knows everyone here and misses the place. She's working on various stuff, star formation, planet formation, astrochemistry. And today, Paola will take us to a journey from star formation to planet formation via all linked via astrochemistry. So we'll be hearing all about this in a few minutes from now. Take it from here, Paola. We can't hear you, Paola. We can't hear you. You're muted. Can you unmute yourself?
Yes, sorry. I started the sharing before unmuting and then it was, okay, so I start over. Let me see. Share, and now I do play. Do you see my slide?
Yes, yes, we see your slide and we hear you well. Go ahead.
Okay, very good. So maybe tell me, Shmuel, if you can tell me like 5 minutes before that the time is ending. So I try
Anna,
to.
so I don't mistake. Anna, what is the 5 minutes? When is the time ending exactly?
Yeah, let's do 20, like a warning after 20 minutes, so for 25 total.
20 minutes from now.
Yeah.
Good.
Right.
Okay, good.
Okay.
I will.
Okay. So I start then. So it's I feel very excited actually to see you all there. So and it's too bad that I cannot be there with you and have some chat with all of you. So what I will do today, I will focus a little bit on some new stuff that we have been doing here, of course, thanks to the great people in my group. And this is really to try to link these various phases that you see in this first slide. So we go from parsec scale down to fractions of parsec, and also to say protoplanetary disk scale. The planet formation that is written here. I will not really go into much detail, but of course there is some link to what I will say about protoplanetary disks, and it is all connected. So I wanted to start actually with but I didn't have much time, too many slides, so I cut it, but I realized that this year is the 20th anniversary of the beautiful CO map that was done, in fact, by Dame Hartman and Thaddeus in 2001. So I hope you are going to celebrate that, because that was an amazing achievement. So I typically start from there just to give a sense of scale of all these regions. But now I wanted to zoom in immediately to the regions that we have been studying since many, many years. And this is actually dark clouds and the prestellar cores. So this is some kind of zoom in into the prestellar cores. That is the initial stage, or say, the object that contains the initial conditions, in a sense, in the process of star and planet formation. So we are going to look into some of new work that we have been doing here. And just to give you an idea, this is the dark cloud seen in this case by Herschel in the dust continuum emission 500 micrometer. And here is in color a 1.3 millimeter dust continuum map that was taken with the 30-meter telescope in Spain. And then here you can see some drawing of the structure of the so-called prestellar cores. We now know that they are very centrally concentrated. And this is also actually thanks to the work that I have done in these particular objects with Eric, who is here, and in the past with Phil. So this is showing that these regions change their chemical structure. And this is important to know because you want to study them from how they connect to the cloud down to the very center where actually the future protoplanetary disk and stellar system will form. So we know that the very center is rich in deuterated molecules. I will not talk about deuteration this time, although it's one of the things that I most like also to connect to the solar system, but just for the sake of time, I will avoid that. But this is just to tell you that if you want to study the very center of this course, you should choose deuterated molecules because they're really good in tracing these inner regions. So what we learned in the past years is one very important thing from observations and also actually in a sense confirmed by theory, just a radiative transfer of centrally concentrated cores illuminated by the interstellar radiation field. We know that the temperature in these regions drops toward the center to very low temperature. This is data taken with the VLA back in 2007. And you can see here that the rotational temperature of ammonia, which we used ammonia 1,1 and 2,2 to measure this temperature, drops from about, say, 10 in the outer part down to about 6 Kelvin. So in these conditions, and we talk about, central density that are above 10 to the 6 per cubic centimeter. In these conditions, you expect to have most of the heavy elements. So by heavy elements, I mean all the species and elements heavier than helium on the surface of the grains. This is a theoretical prediction, but I think we are getting close to actually finding out that this is indeed the case, and I will show you in the next slide. So in these conditions, you have basically kind of an early universe chemistry, mostly with hydrogen, deuterium, and that is, we expect it to be, say, very also easy to follow. On the surface of dust grains, actually what happens in these conditions is much more complicated because you have these thick icy mantles. And of course you keep having these cosmic rays that go through these regions and affect the chemistry and maybe breaking bonds and making more complex molecules. Fine. So what I want to show you now is actually jumping on something that we have been doing very recently with the ALMA. And this is something that I have to actually still circulate among my co-authors. So it's, but it still is in a good shape paper. So we observed in band 3 with ALMA, this one of these prestellar cores, so L1544, which is in Taurus and is very bright and allow us actually to study in detail the inner structure. So we had here something like 300 astronomical units linear resolution. And we measured the deuterated ammonia, which has a critical density of 10 to few times 10 to the 6, so it's very good for this central region of prestellar cores, together with the 3 millimeter continuum, and you can see here the map. And what we found, together, of course, with our chemical models and radiative transfer, so basically we ran a chemical model that includes deuterated molecules, taking the structure of the core as we found with Eric. So this is the Keto and et al. 2015 paper, one of the most recent. And then we ran a radiative transfer on this, and you can see here the comparison between the observations that is in black and the model, which is in red. And these at various offsets from the center of this core. So you see the simulations and the observations are really in excellent agreement. And to reproduce, so these say lines here come from this type of abundance profile for the deuterated ammonia. So the deuterated ammonia tend to have a peak around, say, 8,000 astronomical units and then start to drop. This is the abundance. So the number density of deuterated ammonia divided by the number density of H2, fractional abundance. So, but then you see that at 2000 AU, there is this really sharp drop in abundance. And still from these models, I can ask the question, what is the total depletion factor, which is defined by this equation here. So basically, I want to know how much of these heavy elements, heavy species, heavier than helium are left in the gas phase. And you can see that this is a very small fraction. Within this 2000 AU, we find a depletion factor here of 10,000, which means that only 0.01% of these heavy species are left in the gas phase. So you have to think that at these very early conditions, the amount of ice in these dust grains is huge. You know, we have in fact hundreds and hundreds of monolayers of ice in our simple chemical code. And this is, of course, is the initial conditions of the future protoplanetary disk. In fact, this region has already started to flatten out, and we see evidence for that. But let me move on. Another interesting thing about these prestellar cores is that they are also producing quite a large amount of complex organic molecules. And this, of course, is important for our link to, say, formation of prebiotic molecules and also delivery of this material in the later stages of star formation. This is another beautiful map done by Jorma Harju. This was a paper published in 2020, where he observe the deuterated ammonia again. This is the ortho one. It doesn't matter. They actually follow very similar structure. And this is HMM1, one starless core in Ophiuchus. And you can see that the ammonia is actually tracing here a very well-defined region. This is also where the dust is present. But if you look at, say, one of the simplest complex organic molecules, which is methanol, you see that methanol likes to stay on the side. In a sense, it engulfs the core, but it's mainly from one side. And this is the side that is kind of more obscure from the radiation field that comes from the OB association that is a few parsecs away, say 11 parsecs away from the Ophiuchus molecular cloud. And there is a series of papers now showing that there is a really rich chemistry. We see complex organic molecules that before they were only observed in hot cores in these regions where we know that ices are coming off the grains because that they are heated by the nearby protostar, but now we see them around. And actually, it's not just interesting for the chemistry. I think from my point of view, it's even more interesting because these molecules will give us clues on this connection from core to cloud, which we are still struggling to understand, you know, how the core connects to the cloud and if there is still accretion going on. So this is something, say, for the future. From the point of view of the chemistry, we understand what is going on in this region. Sorry for the quality of this slide, but I like the moving curves, so I keep showing this. So once we had our say observations for complex organic, also in the L1544 core, we decided, this was in 2017, with Anton Vasyunin to actually run chemical models to understand why we see these complex organics at some radius outside the center. Of course, in the center, they are depleted, so they're frozen onto the grains, but they start to form in a very specific region, say at a certain specific distance from the center of this prestellar cores. What is this distance? Well, the distance is exactly where we have the beginning of the catastrophic CO freeze out. So the CO is, as I mentioned already at the beginning, it's, and also the heavier species, other molecules containing carbon, oxygen, etc., freeze out above a certain volume density. And this number is about a few times 10 to the 4 per cubic centimeter, at least in the nearby clouds like Taurus, etc. So what happened in this region where you have the catastrophic freeze out of CO? You have icy mantles that are completely enriched in CO, and these change in chemical composition from water, which hold molecules much more tightly because of its polar nature, to CO, which is apolar in a sense, much lower dipole moment. You have the possibility to make molecules on the surface and let them desorb. And this is what is happening. This is what Anton found here. And this is the abundance as a function of radius in parsec. And we find that, in fact, the complex organic molecules have peaks that coincide with the CO depletion zone. And this, in fact, was something, so we included in the chemistry this measured rate, the desorption coefficients that come from laboratory work from Ministale and Dulieu in Paris, and of course taking into account the photodesorption rate from the work of Karin and other people, and also of course experimental and theoretical studies of neutron-neutron reactions, but I'm not going into these details here. So we think we understand what's going on, so we have a very nice factory of complex organics in these regions. Now we go to later stages. So this is a super simplified version of what is happening in a prestellar core that is magnetized. Of course, you have magnetic fields, so you have ionization fraction. So you have, of course, to take into account the fact that you have basically some sort of ambipolar diffusion going on through this cloud, and rotation, initial rotation of the cloud that of course give rise to a protoplanetary disk. Although it's not so simple, as I said, because in fact, if you consider that the magnetic field, for example, is frozen, it will be very hard to actually make a protoplanetary disk because of the very well-known magnetic braking catastrophe that, of course, you get too much magnetic flux toward the center, you lose the angular momentum, and the disk doesn't form. So we have to get actually to understand how to go from these, say, prestellar cores to disks. Here I put some examples. I mean, some people in the past have been thinking that at the very beginning, these disks are probably self-gravitating because they accrete a lot of mass from the mass in the envelope that is still there in these class 0 stages. And if that is the case, that is actually quite interesting because they can get very hot. And I will show you that in a minute. Now, these are some examples of, in fact, a disk that in the past, actually, when I was in Leeds, we studied with former students about the chemistry of these self-gravitating disks. But now, more recently, with Bo Zhao, who just left, actually, he's now with Ralf Pudritz, but he was with me for several years when I arrived in Munich. So he has been working on non-ideal MHD. And what we did together when he came is to include some simple chemistry in his code. And also, so the simple chemistry was mostly aimed at following the ions, because we know ionization fraction is so important in this contracting magnetized cloud. So what Bo did was to implement the grain size distribution, the usual cosmic rays that ionize, and you can also change this parameter, the flux of cosmic rays, and you can change the initial rotation, mass to flux ratio, and all these parameters. But we noticed that actually a very important parameter was the grain size distribution itself. So for example, we tried assuming that the small grains are actually, say, gone from the gas phase. We didn't actually follow the coagulation of the grains self-consistently, but we just truncated the MRN distribution, so the grain size distribution that we were using, avoiding these small grains. And we noticed that some kind of magic happened, because these dust grains are really well coupled with the magnetic field. So they are the ones that mostly drag this neutral and say in the center together with the magnetic field and slow down the contraction. However, if we remove them, we can actually get much higher diffusivities in ambipolar diffusion diffusivities, and then this reduces the magnetic flux in the center, and we can form a disk. So just to give you an example, in the top you have the one of the run with these very small grains, and you can see that it's all really chaotic, and at the end, okay, you can have outflows, but very tiny plumes, no disks at all. But without these very small grains, you could form actually relatively large rotationally supported disks and also self-gravitating disks. Now, I'm not going into these details, but just to tell you that, in fact, we then studied with Kedron Silsby at MPE this question of do very small grains deplete fast in molecular clouds, and more importantly in dense cores. We are mostly interested in depletion of them in these high density regions, so just before protoplanetary disk form. And the answer is yes, as long as you have this drifting of material due to the ambipolar diffusion, so the small grains actually get stuck on the larger grains. And this was shown. This is one of the figures of the paper by Kedron Silsby that appeared last year, where we show the distribution, initial distribution of the grain size, and then depending on if you have ambipolar diffusion, yes or no, and if you have some turbulence, yes, so this is a sonic turbulence or no turbulence. Of course, you have different changes in this grain size distribution, but the final conclusion was that it is very efficient to have these small grains depleted. So these models that Bo did, from my point of view, of course, I'm a little bit biased in this case, but they are really, provide the good understanding of disks that are now we are seeing with ALMA, in particular. So these are the simulations from Bo, just changing a little bit, for example, the initial cosmic ionization rate, you can, or these very small grains, and you can make, as I said, the self-gravitating disks or fragmentation, and this in fact has been seen, and these are beautiful data from Felipe Alves that he took with ALMA.
Paola, I just wanted to say a few minutes left.
Yes, thank you. Yes, I don't have too many more, I think. I lost the track. So here, this is a very recent paper that has been just submitted from my student Joachim, and this is Joachim Zamponi, who has been working with Maria Jose Maurera, so there is indeed, so this is a new point that I wanted to bring. So we have been observing with high angular resolution one of these class 0 famous disks that is in Ophiuchus, IRA 16293. This is one of the sources. It's a triple system, and this is the northern source. So with the high angular resolution here, you can see the beam. This is the 20 AU. 3 millimeter is even higher resolution than 1 millimeter here with ALMA. So we have very bright fluxes, and actually, yeah, the brightness temperature can reach, say, 400 Kelvin toward the center. Now, we tried to actually simulate, so to have the simulations, observe these simulations, and see if they match the data. And in fact, what we found is that, okay, this is not actually the observed simulation, because I had to choose which figures to show. This is just the simulation itself. Is a slice that we see, say, face on and also edge on, showing actually the temperature of the gas, and the gas and the dust here are coupled because the densities are very high. And so if you exclude the very center, where the code actually doesn't have enough resolution actually to look into the structure, temperature structure, we see that to reproduce the fluxes that we observe in these sorts, we need to have these self-gravitating disks that are heated by internal shocks produced by these spiral arms that are actually formed because of the self-gravity. So the disk can be really hot. And so by hot, I mean really, 500-600 Kelvin. And we see this evidence of increase of temperature toward the midplane. So the midplane is hotter than the outer part of the disk in this case, so in these very initial phases. So I'm not saying that all the disk will be like this, but at least some are like this one, which means that all the material, all the molecules that have been accreted in this central region will be, all the ice will be evaporated, and there will be some kind of strong reset. And this is the big thing, because, then one say, okay, then who cares about this prestellar core chemistry? Because, you're just telling me all these thick ices and then they're all evaporated. Well, I think it's not the end of the story, because in fact, these regions are not so in this class 0 stage, you still have a very massive envelope with material falling down continuously. And we see actually evidence of these large streamers. And this is the work of Jaime. For example, in PERM2, this Perseus class 0 sorts, where there is a very well-defined outflow that was mapped with SMA, this by Stevens et al. In 2018. What Jaime found using NOEMA, actually I have a better picture of this, is that, for example, HC3N that comes directly from the cloud surrounding the envelope of the protostellar object. This material is flowing toward the center, and Jaime made a model for this, actually showing that the velocity that we see is consistent with this kind of, inflowing material from the cloud. In fact, HC3N is not abundant at all in evolved clouds. It's an early type molecule, so it must come from regions that are, say, more farther out. And you can see that the direction of the streamers is completely different from the direction of the outflow. So the two things are not going together. Very recent stuff that is still in work in progress. So it's the same sorts now looking with NOEMA. In fact, we have a larger project that covers 32 class 0 and 1 sources and also 8 class 2 sources. This is the project together with Thomas Henning, so putting together MPE and PIA, where we see, in fact, that the disks, so the central region, say the inner envelope, let's put it in this way, is very much affected by these streamers that we are finding at large scale. This is all with NOEMA. Other streamers, so not just in class 0, but even in class 2, where you don't, or say this is actually a class 1 to 2 sorts that has been recently observed by Felipe Alves with ALMA. There is no envelope here. There is a nice, beautiful disk that is seen at John with the nice cavity, but you see with the CO 221, beautiful streamers that again bring in material into the disk. So even if you have this initial phase that basically evaporates everything, you keep bringing in this cold, icy stuff from the envelope and the cloud. And of course, this will affect the dynamical evolution of the disk. In fact, these streamers may even, this was suggested by the Nature paper by Segura Cox et al. In 2020, in collaboration with several people from actually also CFA, where it's obvious that if you have these streamers, asymmetric flow of material, they will input asymmetries and create, say, substructure in the disk that may even promote deformation of say rings and also maybe planets. So this is my last slide, but actually this work is from Drozdovskaya et al. But it is just to show that, in fact, I think there is still hope about this, say, inheritance of material from the cloud to the disk and future planetary system like our sun, because this was the comparison between organics and in the famous pills. So this is the IRA 16293 system and the comet, showing a very good correlation that in fact the author said that the volatile composition of cometesimal and planetesimal must be partially inherited from pre and protostellar phases of evolution, and other work that actually we have done for phosphorus-bearing molecules. This is with Rivilla et al. In 2020. So this is the conclusion. I think I'm over 1.5 minutes, so maybe I stop here and I discuss with you. Sorry for being late.
It's fine, it's fine. So
thank you.
Thank you so much for these very interesting results. So let's see if there's question, and I can already say that I hope there's not too many, because I have lots of questions, and if there's not too many questions, I will ask you many questions. But let's see if there's other people first before I start with mine. Okay, so Phil Myers, I see, want to ask. Yes, go ahead, Phil.
Okay, can you hear me?
Yes.
Yes, very well.
Right. Well, lots of really interesting results, Paola. Just one particular thing I found intriguing. Do you have an estimate of the mass accretion rate due to the flow in the streamers? And also, how does that compare to the expected rate from the disk?
Yes, let me see. So it's a little bit, how to say, I tell you the number, and then I tell you how we derive that, because we have not yet we need to find, say, a more accurate, I think, way to measure this inflow rate. So we found, for example, in this particular case here of using the HC3N, an inflow rate that is of the order of 10 to the minus 6 solar masses per year. And so it's not so different actually from what you can expect for at this say age of the cloud. Now here there is the assumption about the abundance of this molecule, because we only have here one transition. So we are trying to actually refine this type of study to actually have a better estimate of the volume density, for example, from a multiple transition of the same streamer, and try to understand better the mass. But from this that has been, say, studied more accurately so far, we have this 10 to the minus 6 solar masses per year.
Now, is that based on kinematic, Doppler resolved motions, as well as abundance estimates?
Yes, exactly. So we assumed abundance with respect to H2 for the HC3N that I think was, so we look, at some typical abundances of HC3N in molecular clouds, which of course is different depending where you look. And so we took an average of that and we assumed that as our number. Here. So I don't remember now, I think it was something like 10 to minus 9. So, you could have some error bars there. So we are trying to do better in this, for this, because that is very important. So it's something we really need to find a better way.
Okay, great stuff.
Thank you.
And Paola, just to continue on Phil's point, so could the non-equilibrium chemistry help in determining the time scale and then refine these accretion rates? So, for example, you look at these different molecules and you see how if they're in equilibrium or how far from equilibrium they are, and this gives you an estimate of the time scale they've been in the region.
So I think, yeah, that's a good point. I tell you what I think is going on. And again, we have a follow-up project actually here observationally to test this idea. So I think the HC3N is actually coming from the cloud that surrounds, so I think I mentioned this earlier, from the cloud that's the lower density cloud that host the core in which this protostar has formed. So the cloud is probably, you know, has an average density, volume density of the order of 10 to the 3, few times 10 to the 3 on average. We are in Perseus, it's very, you see lots of filaments, filamentary structure on average, the densities of the order of 10 to the 3. 10 to the, maybe, you know, between 10 to the 3 and 10 to the 4. I cannot tell the exact value. Okay, yeah. But at these values of the density, chemistry, let's say, is, and also you still have some photons from the interstellar radiation field that partially, say, dissociate the CO and can liberate carbon. You can keep some kind of, I think, equilibrium abundance of HC3N around, together with CO and other molecules, because it's just, you know, this CO dissociation, photo dissociation, and formation of carbon chains that at some point equilibrates, and you have it there. And then if this material is actually coming, basically funneled down inside the dense core, you know, you can have some time scale, so it cannot survive too long, because again, you know, it takes but still it can take about definitely more than 10,000 years to be transformed into CO. So this is not what we see. So this must be something much, say, younger, this streamer, than that, okay? But it is really directly coming, doesn't have the time to actually evolve chemically within the core, and it is directly transported, say, onto the disk, or anyway into the inner envelope. But I don't say, because of course we are looking into this interaction with the disk. We have some high angular resolution data, but it's still a work in progress, and it's not yet so clear. But definitely, you know, as I show you in the next slide, there is already in this sort evidence from our preliminary data from NOEMA that, for example, the DCO plus and 2D plus that are very good tracers of cold gas, they are distributed differently, and we have some kind of hole here that we believe is probably the region where this flux is, this streamer is impacting. But you see, I mean, I didn't say much about this because we are working and on this, and we need to find proofs, mostly shocks indicator, and in fact there is a good indicator, which is the the SO line here you see in green. So there is some evidence of shock, but I'm not yet completely convinced, so we need to get into more detail. Yeah. But you know, yeah, that's sorry for the long answer.
No, this is exactly what I meant with what you said, that there is some time that it couldn't be too long. Otherwise, you'd expect a different chemical composition, which you do not see. Because yes. I had a similar problem and idea on larger scales. Maybe I'll mention this in a moment after I verify that there's no more question. Actually, Anna asked a question on the larger scale, Anna Bonaccia. So Anna is asking, what about the impact of the large scale structure on the structure of disks?
Right. Yes. So indeed, you know, this is really now telling us that even this map here, which is done, you know, this is a few thousand AU, is not enough. We need to move further. So because this is the, say, primary beam that we have with the NOEMA. So you see that there is still emission going on here. So the plan now is, and we have already, Jaime actually has submitted a single dish proposal to do a larger, say, map of the region in HC3N to really follow these to the kind of end point and see. So what well, again, I mean, I don't like to say things when it's not proved, but I think that what is going on is that we know that there is, so all the interstellar medium, and, you know, thanks also to Herschel, but even before Herschel, we knew that molecular clouds are highly filamentary, and you have all kinds of filaments connecting basically these cores that are kind of mini hub, in a sense, using some description also from field work. So you have this material that is actually flowing, connecting since the origin, say this little hub that we call dense cores, to the larger scale structure. And so this is probably what is going on. I mean, if these filaments are actually connecting, you know, material from the outer part of the cloud or the less dense material, they're bringing in new stuff. So new, say, young chemistry that is enriching in this case, the inner envelope. So it's definitely, yeah, this is something that we are doing, and I cannot show you anything yet.
Mm-hmm. Okay, so actually, I had several questions, and I just start with the one that is most connected to the last sentence that you made. And this is, what extent the molecules that are forming, how important is it to understand the formation in the ISM clouds, or most molecules form later on in the, you know, in the denser stages? So, like, for example, water or other molecules? So I've worked on water, but there are of course more complex molecules. And when, for example, when I worked on my work on water in the early universe and things like this, I was interested to know whether it is even important or interesting to know that water has formed in the ISM clouds, because in any case, as a cloud collapse, maybe then the chemistry initiates itself and then the molecules forms later. So what is it? Do they mostly form at the earlier stages of cloud, or already at the later stage when the star is forming and the planet are forming?
Right, yeah, so the molecules form very early. You know these, come on. You don't need to
I know they are there. But let's
yeah,
say
they're there.
let's say
So,
you have a cloud with no water, because let's say metallicity.
Okay.
Or you have water. Is it matter at all? Because one may say it doesn't matter. In any case, when the cloud collapses, it becomes dense, and then everything.
You're right. So, well, okay. So let's assume that we start from what? Diffuse cloud. Let's not go to the warm ionized medium. Let's start with the diffuse cloud. So we start with the diffuse cloud, and you already have actually some chemistry going on, because we see actually molecules in absorption if you look at along the line of sight of quasars. Okay, so definitely there is some CO. Of course, it's highly photodissociated. So most of the carbon, of course, is in C+. But you still, you do some chemistry. Of course, you make H2, which is very important. So you have H2 in these diffuse clouds, at least, you know, 50% of the hydrogen. But so what and you also have some chemistry, some carbon chains. C3H2 is seen, formaldehyde is seen in absorption, HCO+, lots of molecules actually. Even I saw a paper not too many years ago about formamide, which is a complex organic molecule. I don't know what was going on in these observations, but anyway, there is active chemistry. And I think, you know, the surface of the grains, this amazing capability they have of catalyzing molecules is just amazing. And you have, and I think what's going on in diffuse clouds already is that they are not just, you know, uniform diffuse cloud. They have already some kind of substructure, and in this substructure you form molecules. As you move to more extincted region, of course, you start to form more molecules, in particular water, because water you need to have to be screened by the UV, no? The interstellar radiation field. So you start growing these ice mantles, and then eventually, when the density becomes high enough, there is this catastrophic CO, freeze out. And that is very important because that adds on top of the water a lot of this carbonaceous material that can be converted into methanol. CO can be hydrogenated up to methanol. And this is the starting point of many of these oxygen-bearing complex organic molecules. So, you know, it is going with the evolution. The other thing that it's interesting is that the carbon chemistry and the nitrogen chemistry, for example, are different. They are, say, they have some kind of one order of magnitude, say, out of phase, in a sense that the nitrogen takes longer to form. And this is why we see these peaks in the nitrogen-bearing molecules in the dense cores that are, you know, particularly dense compared to the surrounding. So there is an evolution. So I would say carbon and oxygen-bearing molecules form very early, but the nitrogen, for example, organics, you need more time.
Yeah. By the way, meanwhile, I see Andrew Burkhardt is raised.
Ah, yes, I see the hand.
Yes.
Hi, Andy.
Hi, Andrew. Good to see you again.
Nice to see you.
Excellent talk. Yeah, I had a couple questions kind of building off a little bit on this. So when you're talking about these, you know, streaming in of material, for example, for like HC3N in from these large clouds, theoretically, you're also going to be streaming in dust and ice in there as well. And theoretically, the environments that those ice are forming are going to be different than the ice that is close to these, you know, kind of protostar, you know, protostellar objects, be it cosmic ray flux or UV flux or something like that. Do you have any thoughts on how you're kind of enriching a different type of ice chemistry into that scenario as well, not just the gas?
Yes, I'm saying yes, but actually I don't know. But it's very interesting. Yes, I have thought about that in a sense that it's definitely true that also now we see these long streamers in class 1, class 2, and also in HL tau. I think there have been observations. I don't remember now the first author, I'm sorry, but there have been observations of streamers. So you keep carrying in material into this disk, even in the later stages of their evolution, from lower density materials. So you keep accreting dust grains, as you said, that will have ice composition that is different from what it has been in the inner envelope of these protostars. So this means that at the end you will have a mixture of these. So you will have a mixture of, you know, for example, as I said, I didn't talk about deuteration, but you will have a mixture of highly deuterated and very low deuterated ices. And the fraction of these two will depend on this accretion, how long this accretion from the cloud will continue. And of course, this will depend on how much material will actually be kept nearby the star. So I guess, you know, if you have a big cluster, this material will be blown away. So you're stuck with your original ices, while if you are in a more quiescent region, you can keep actually accreting this material and being actually enriched in these carbon chains, which are also very important for prebiotic chemistry. So, you know, it's all, in a sense, we don't want to be stuck on the idea that once you have your core, everything is there, and this is the end of the story, and you can build your life or, you know, your prebiotic molecule from that.
Yeah, no, that was that is kind of what I was wondering about both the deuteration side and also the that would also probably change the structure of the ice itself, of whether it's crystalline versus amorphous as well, and that's gonna kind of have a lot of effects. Can I ask one more question? I know there's another one on there.
Yeah, maybe I'll just go to Charlie and then back to you. Okay.
Sure, thanks.
Hi, Charlie. We can't hear you. Can you unmute yourself?
Hello, Charlie.
I think you're still
yes, unfortunately.
Probably double. We cannot hear you. Maybe no, we can't hear you.
It seems, but he's not muted.
He's not muted. Maybe it's on his computer or something.
Maybe the computer.
on the computer. Maybe Andrew, Andy, maybe you can ask your question while Charlie is trying to fix this.
Sorry.
Charlie, meanwhile,
Sure.
try to fix this, and we'll have another question from Andy.
Sure, yeah. The other question, so on this work you're talking about these this hot protoplanetary disk where you're potentially seeing these sort of different sorts of shocks, do you have some more information of like what types of shocks are we talking about? I know you mentioned you know, these really high temperatures that would thermally desorb things off the ice, but obviously also there's going to be non-thermal desorption processes and other kind of classic shock tracing things going on in there as well. Are these like, what sort of speed shocks, or are we talking like C shocks, J shocks kind of stuff, or?
Yes. Okay. So need to be careful because again, some of these models that are so these models simulations of self-gravitating disks are actually you know, need to make some simplifications to be able to run to a reasonable time, and one of these simplification is in fact really on these shocks, because to resolve the shocks you need to go to super high resolution. Of course, this can be done, but has not been done yet, and I'll be super interested in doing that. However, I think, so of course, if you have these shocks and if you resolve them, you can actually look at the sputtering, you know, the grain-grain collision, you can have vaporization of grains, which, you know, will change, not just, will change the grain size distribution, will change, you know, several properties of the dust and gas. But I think it's already clear that if these disks exist, and I think we have this proof now with, there is also some other paper actually from, originally this disk was observed by Laura Perez, and so there is her former student now is working on that. It seems that now we have some proofs that these self-gravitating disks exist. They may not be everywhere in all class 0 sources, but in some exist. And if this is the case, the temperature is so high that you will anyway get complete evaporation of the ice. You may even evaporate carbonaceous grains, because the soot line is actually, you know, it's the temperature is probably, you're talking about 300-400 Kelvin, and this temperature are seen there. So you may get rid of the carbonaceous material, and this is something I think that we need to be followed up. This is so interesting.
Yeah.
So much to do. Oh my gosh!
Very interesting. Also, I hope I'll have a few minutes to ask you another question on this. But first, let's see
if Charlie can speak.
Oh no! Charlie, maybe you can type.
Write something in the chat.
Question, and then I will narrate it if you can type it in the chat. Meanwhile, I'll just ask a small question, and then I'll go to Gary.
That is yes.
Yeah, Paola. So for the hot disks that you mentioned, you actually showed very high temperatures, even like as high as 1000 Kelvin, or I don't know, a few hundred Kelvin. No, just
yeah, several hundred Kelvin. Here it is. So as I said, in the very center here, don't look at that, because there are some numerical problems. We are not really resolved. There is some problem with the resolution here and the extra viscosity due to the.
Because at such high temperatures, I would expect already neutral chemistry to be efficient, and some, I don't know, maybe excitation of, okay, at 100 Kelvin not, but if it reaches 1000 Kelvin, even excitation of H2, and then you might get H2 lines, like infrared lines of molecular hydrogen.
Oh yes, yeah. I mean, you have all kind of shock chemistry here going on. We have not, you know, this is something definitely to do. There was this work, as I said, mentioned from Ailey and other people in Leeds. Also, Mark Evans did some work on the chemistry in these regions, and yes, you can have a very rich chemistry here. And so we are talking about the temperature that of the order of 400-500 Kelvin and even higher. But let's say 300-400 Kelvin, which is this kind of nice number for this carbonaceous material that it's quite interesting. I think this could interest Ted Bergin with his missing carbon, and try to link with the Earth. Okay, sorry, maybe.
Gary.
Can you hear me?
Yes, Gary, I can hear you.
Hi, Paula. It's great to see you and hear you.
Thank you. I don't see you though, but fine.
Well, I'm sparing you that. Consider it a favor. Oh, it's just when you have video going, sometimes your voice breaks up a little bit because of
okay.
but I was wondering if you have, you have this model in which, for example, the ices are some combination of reprocessing in the disk and material that is freshly brought in from an extended envelope. And I'm wondering if you've compared this model with comets in our own solar system, where we do have measures of D to H ratios and other compositional information.
Yes, that's very interesting suggestion. In fact, I think in a sense this goes in the same direction as Andrew question before, because in fact, I mean, so the answer is no. I have not done that yet. But indeed, if we can quantify a bit better, this amount of material that is, say, inflowing, and this is, as I said, the work in progress, it will be, in fact, I think very important to do this connection, because we know that there are variations also between comets from the same family, Jupiter comet, Jupiter family, or Oort cloud comet. So there is quite a lot of variation, and it'd be nice to see, in fact, if we can understand this mixture just from the point of view, of this mixing the ice from different sources. And I guess that if these flows come in, I'm not sure how well they will mix up with the rest of the, of the inner envelope and the disk. They may even, just enrich locally apart. And so it will be something to do, but I have not done it yet. It's a great suggestion.
One other thing I'll mention just briefly, I forget if I've presented this at a conference where you've been in attendance, but we're working on a mission right now. It's approved, and we're in phase C, that will look at potentially millions of lines of sight in the Milky Way, doing absorption spectroscopy of ices. So what we hope to do is to establish a very statistically significant evolutionary path between diffuse cloud ices all the way down to protoplanetary disks. So it is our hope, we'll see if we can realize it, that in a few years, we'll have these millions of absorption spectra.
Yeah, that'd be great. I mean, to have it. What is the name again? Is the sphere?
SphereX.
Yes.
Yeah.
Yes. So yeah, I remember you mentioned that, and it's a very exciting project. So I really hope that will go through, because then we can compare the ice with the gas. Finally, we can constrain our chemistry, because that is one of the problems. Many molecules actually sit on the grains, and we have lots of uncertainties on the in-surface chemistry. So we really need observations of the ice composition. Of course, now with JWST, we hope also to learn a lot about that. But having such a huge, say, survey, and basically, will you survey the, I don't know, galactic plane or?
Yes, well, just very briefly, SphereX will map the entire sky. And so when we're not looking at the Milky Way, we'll be doing cosmology, but we will cover the entire Milky Way. And what we'll focus on are those lines of sight that aren't confused, that have, that don't have multiple background stars within a 6 arcsecond pixel, and show evidence for a line of sight absorption. Yes. So that could number in the million, in the few millions.
Great.
And we're building it. I mean, it's not a proposal, it's hardware that's being built.
And will fly when?
It looks like now it was a bit, we originally were going to fly in 2024, but because of COVID related delays, it will probably be in 2025.
Okay, so relatively soon.
Something to expect to wait for. I think we're officially done, but finally I got the question for Charlie, so I thought maybe I just say so that we end on a positive note that we succeeded to get the question for Charlie, and that is, Charlie is asking for clarification, which organics are formed primarily in gas phase versus on grains? For example, is the H3CN that Jamie sees falling onto the disk formed in gas phase?
Right, yes, that's a good point, a good question, Charlie. So HC3N, we can reproduce its chemistry just with gas phase chemistry. So there is no need of, say, dust. So to answer your question, I think in a quick way, is that every time you have a saturated molecule, so highly hydrogenated with basically like water or ammonia is a little bit different, so sorry, maybe this. But for example, the best example is methanol. Methanol, as far as we know, there have been lots of attempts. There is no way that you can form a methanol at the abundances that we detect without surface chemistry. So you really need CO freezing out and then hydrogenate until it is saturated and it is formed. And that is basically the unique route of methanol. There is no gas phase route. There is, you have to protonate it and then it can dissociate and form methanol again, but it's not really, I don't consider that an important route. And the other one that is very important for the chemistry are all these saturated molecules that contains lots of hydrogens, because to have many hydrogen atoms in molecules is very inefficient in the gas phase. So you really need to have and while on the other hand, on the grain surfaces, once you have hydrogen atoms landing on the surface of the grain, it will be this most efficient thing that ever happened, very fast, a fraction of a second, it can hydrogenate whatever it can be hydrogenated. So for example, water, of course, the majority of water is formed on the surface of the grains. And then, of course, you can also form it in the gas phase through other ion-neutral reactions, but that is much less efficient than the surface. So I would say, look at the hydrogen numbers and then say that will tell you if that is gas or surface. And if you have carbon chains, that is difficult to form on the surface because these heavier species, so you have to have multiple carbon, they move much more slowly on the surface. So they actually, the ion neutral reactions are in this case faster than the surface chemistry. Yes, so it's
then in the warm disks you also have the neutral reactions, which become
but actually you have them. So the neutral reactions, Shmuel, are also present in cold regions. You know about the work that has been done by I mentioned it by Shannon and well, okay, I have to go back here. So I mentioned the names here. So this is the Shannon 2013, and this is the group actually from Leeds. I was still there when they did this. It was such an exciting thing. So they found that the rate coefficients of neutral reactions, especially the one with the OH, actually get much more, say, much faster these reactions at low temperature, because the two molecules, say, approach each other, and if it is very cold, they form a hydrogen bond complex that is long-lived enough to actually have the tunneling with the hydrogen of the OH and actually form, say, a new molecule. And so this is actually very important discovery that was done in this, and then followed up by Balucani, Skalperis, and other people. So it's not just, but of course at high temperature.
Very surprising.
Yes, yes, it's look at this paper, it's beautiful.
Okay. Okay, so I think our times is up, unfortunately, but it was very interesting. And Paola, I'll be happy to continue discussing some of the stuff that I didn't have time to ask during the colloquium.
Sure.
I guess at this point, I'll say everyone, thank you so much for coming. And
yeah, thank you all for spending 1 hour with me. And I really hope to see you soon for real.
No, we're very grateful for you sharing your time, and we know that the world is more complicated than ever right now. And it's
exactly, yes, yes. But it's
a
great
lot to be
see
grateful
you all
for.
well.
That's
and,
right. That's right.
That's fantastic. So thank you for invitation. I have to stop the sharing actually, otherwise you will be stuck. Okay, and see you soon, I hope. Bye-bye.
Yes.
bye, take
Thank
care,
you.
everyone.
We wanted to say thank you, to everyone for your time this semester. Shmuel, that was great. Thank you.
Okay, thank you. Bye.